So welcome back. Let's keep going with our program. So now we'll have a talk from Yu-Feng about the framework for Federal Global Ensemble Digital Terrain Model. So Yu-Feng is a researcher at OpenGeoHub. He is leading work with the DTM and LiDAR data. And yeah, he just decided to become a PhD student now. So yeah, it's a long road for him. And yeah, the floor is yours, Yu-Feng.
Okay, thanks for my supervisor. And now today I'm gonna talk about the framework of Federal Global Ensemble Digital Terrain Model. So first of all, I want to introduce the digital elevation model to those who don't know yet. So a digital elevation model as DEM is a digital representation of the terrain elevation for a 3D of the global surface with the height. And it's especially useful for some process-based model, for example, model soil, model water, model erosion stuff, and also model something related to biogeography, for example, where the species were located at and where the animal species or tree species are located in that. So basically that's what the contribution to more Earth observation. And we were put in here as in OpenGeoHub, we do tons of global modeling. And for digital elevation model, it's a very good, it's a piece of interpretation for the Earth system. So for example, here is the soil mapping frameworks. So we do terrain elevation model with vegetation and climate, these three components to actually provide the information as covariate to map the more advanced indicators like soil properties that Tom will introduce in the next talk. And the questions there, why we need an ensemble digital terrain model. What is this ensemble? So this is the Earth pictures of it's a before and after. As I don't know what the time frame should be, but apparently there's a lot of satellites circulate around the whole world, and so many data and information has been collected and need to be processed and provide useful information for us. But it turns out to be kind of overwhelming for most of the scientists if they are first into this domain, or they has been working a domain, but new technologies keep coming and need to keep tracking on that, especially for some of the stuff they are not familiar with. For example, so for soil mapping, you don't really focus on soil mapping, but also mastering geomorphometry, geomorphology, for example. So also in digital elevation model, there's tons of product has been collected and published. So for example, from the early age of the SRTM, the NASA team also have the Esther GDTM and NASA DTM. And derived products, for example, like coastal DEM and MERS DEM. And from the JAXA, they have AW3 D30, also the digital elevation model. And Airbus and DLR, they have TandemX and Copernicus them as the most recent global elevation, official global elevation model could be. And according to the Copernicus DEM, you have a lot of other digital terrain model which remove the vegetation and buildings from Copernicus DEM, for like the Olivian DEM, Delta DTM, and FABDEM or FATEM-DEM. And for the commercial product, you have DLR that produce this World DEM in 5-meter resolution. So there's a lot of different elevation model already exists that hard for researcher not in this domain to choose. So there's people in our community dedicated to do the work comparison up to find the best global digital elevation model actually. So there's a few publication leading by Peter Goff and also Peter Strobel to initiate the DMIX projects to compare different digital elevation model in different use cases. So there's already seems to be a need to actually understand how different digital elevation model works. And this is the summarize actually done by me to actually go through all of the digital elevation models. So the first of all, we can see it a bit like a center. The name is a bit wrong, but the best accuracy actually talk about what is that for the best accuracy. So the green dot is the digital surface model, which they flew, for example, SARS data above the surface, but they capture on top of the canopy, assumably, and on top of the building to actually record the height. And digital terrain model, on the other hand, capture the bare surface. So in the idea is they remove the vegetation and remove the building to actually represent the bare surface. And that has been kind of show that's better for hydrology analysis, also soil process. And this is for what the elevation model means. They have surface model and terrain model. And now we are focused on terrain model because in surface model, for example, we have AW3D30 and Copernicus dam. They have already open access for community to actually require them to use freely. And for the digital terrain model, on the other hand, we only have non-commercial license, for example, FATEM and FAPDEN, and also commercial license from the World DEM. There's no open data actually for the community to actually use that, provide service, and derive different products. So that's what we see in this project. Free data should be embellished and used. So that's why we create this global ensemble digital terrain model in 30-meter resolution, and here's the publication. So that's what we have done, and it's just published 2 months ago, I believe, when I was in holiday. And this model assembled different digital surface model, this AW3D30 and the Copernicus DEM. These two open source data, which can be derived to another permissive license that don't require any extra charging or licensing issue, or kind of, you can alter the license whatever you like. So that is the main output of this research. And also we derive different terrain variables that according to this digital terrain model, but we are not discussing here. And since it's open source project, we also create this GitHub issue, GitHub page. So it's actually working. You can see that there are some people posting issue that ask me to fix some problem or changing or kind of improving the data. And then we try to keep this as active as possible so people can contribute in the community, but also, interacted and receive the up-to-date information as fast as possible. That's what we do in OpenGeoHub. And we also make several webinar. And also I have a presentation of this digital terrain model in the Living Planet Symposium this year. And so we put up data in this map, the first fully open source digital terrain model product at 30 meters. And after that, I was thinking about what should we build upon that, because this is, you can see these differences as FATEM or World DEM. FATEM, by the way, is still the most accurate digital terrain model. They published the paper maybe 5 days before me, so I didn't really change the model because I was working on polishing already. But they also have a very good accuracy, but they have non-commercial license, which means that you cannot derive product only for research. And let me dull a little bit, and also I put it in my paper to compare this World DEM Neo, so produced by DLR and Airbus, that they have this 5-meter resolution DEM, digital terrain model already, and some places 12 meters. And do we really need something at 30 meter? And as there's already a commercial product you can purchase in 5 meter, and you can just simply resample for the whole world for your study area. So you don't actually have to use this 30-meter product, since that there's the better product there out there as a commercial surface that you can use. But for the open source, the open community, what should we position ourselves in this ecosystem? So we are kind of like brainstorming a lot, and I did that today. This morning, I was checking online some information, and we saw like there are people like using our data for like web application, and there are already some tutorials so using our data to teach people how to access this data. And even like in Spanish and Arabic, I don't understand what they're talking, but they use my data as an example to access to the crowd surface. So this was actually quite interesting that actually a lot of people interact with our digital terrain model and in this community. So at the end, I would really deeply think that we should, how can we bring more people into this community? And back to, so that's why we start doing this work. So back to 2003, me and Tom and I have already tried to do the global ensemble of different digital terrain model from the actual terrain product and also national digital terrain model. So to do not even global, but also ensemble with the local, national, or even state airborne LiDAR data. And we actually get some great results. And then we have another link, but at that time we didn't go too deep into it, but we have a really good response of that. But there's also another story after that, which create this initial to create GDTM 30, but it will be the story after all. So you can ask me after this if you're interested to it. Yeah, so as published this paper, we also try to see if we can assemble national or different global terrain data, because at the beginning of this global digital terrain modeling, we only use the digital surface model from Copernicus and Atlas to map the terrain. And for the next step, we were thinking that, for example, here you can see the reference data. If you see the clean patches, compared with our global EDTM, our model actually didn't perform that well on this area. So we tried to see if we can incorporate our digital terrain model, which is also open source, which is open license, but maybe it doesn't cover the whole world. For example, this delta DTM, and then we derive 10% quantile to see that it actually can improve our predictions or our map in the closer area. And this has been visually quite a good success. If you see, you can actually compare these two. They have been removing a lot of noise from our global global ensemble digital elevation model. So there was already some tests in the publication, and we just and then we are trying to improve that after all. So that's what we are currently doing, and this is also I will give a workshop tomorrow about this. So basically, there's the idea to actually use all of the global digital terrain model, which is open source, and adding different places with not the full global coverage data from, for example, national then or state LiDAR DTM to create an ensemble, easy ensemble way of GDTM, and we call it GDTM plus. So it's not the original, it's not update every pixel of the GDTM 30, but some of the coverage that will be updated. So this can be a process loop that every time we receive a new GDTM 30 plus, and they will go back to an ensemble with another national. Then if the new data resources pop up or new people who are willing to contribute the data, they can always join into this process loop to produce a GDTM 30 plus, as not every pixel has to be altered, has to be improved, but gradually update and improve our product. And also interesting thing that this project can be also create the data DTM products as non-open license. So you can alter the license if you merge with your private LiDAR DTM and you wanted to make it commercial product. And you can just simply take this GDTN30 and then create a commercial product out of that and sell this for people who need that. So this is our actually the framework of creating this data sets as the hub that people can always contribute and do in this update loop to improve the product at the self for public community, but also create commercial product out of that. And we already see some web application using our math as a base math. So using this framework, they can more interactive with the community for actually have more usage and serve more people in a different way. So this is the last slide, and this slide is actually just a tribute to this project, which it's located to one of the use case that we have working on in OpenGeoHub for the global topographic and hydraulic surface. And so yeah, if you're interested in tomorrow, there will be a workshop that talking about how to actually make this data, access this data and actually work with this airborne LiDAR in not just 10% quantile, but different way to see if we can get some improvement and also testing out. So that's my presentation. Thank you.
Thank you, Yu-Feng. Do we have questions?
Thank you for the presentation. Yeah, very interesting. The part that the LiDAR data are being used and all this, and make it into global model. So I'm very curious about. Okay, you talked a lot about spatial resolution. How about temporal resolution in terms of how often do you think that the LiDAR data should be collected? And then because you're collecting national level or European or global, and then the commercialized one, it's good that if you make it to use this commercialized one, the spatial resolution might be improved. But how often do you get it from them? No, I mean, I don't know if you understand my question. Okay.
So there's a lot of continuous discussion in the geomorphometry community about to do a spatial data kick of the digital terrain model. At the first thing that it could be quite straightforward. I just collect the data and I give it like a timestamp. But in practice, actually, the national digital terrain model that every different country gave. For example, in Taiwan, we have the digital terrain model, but the western part and the northern part and the eastern part and the southern part are collect in different years. And they have to give the range of, okay, this is this period of the digital terrain model in this resolution. And to actually collect all of the national DTM, you have to always check their spatial, like temporal coverage. And they usually just give you the time when they publish. They don't really go specified when did they collect the LiDAR data points. And so it has been tough to do that. And one of the simple way to think about that is we are actually producing this terrain model, which could be less sensitive to the land surface change, because except for like landslide or earthquake, the terrain actually crafts very slow by water and things. So if you do like 5-year range, that's an update for the whole like period. It could be could detect something like meaningful, but yeah, it has been the continuous discussion inside the community, and I'm also trying to figure out if there's a possible way to actually give all the pixel a record of the date, and also keep the old version to see that there's the terrain change of that, but without actually be a data producer, actually who flew the LiDAR data, it will be not consistent. So yes.
So continuous discussion and investigation. Okay. Yes. Okay. Thank you.
Yeah. Thanks. Nice work. I was just wondering, how do you consider the uncertainties from the global models? Because my question is, wouldn't it just be better to replace areas wherever you have ALS data with the ALS data or other data? Because all the global data sets you're using, none of them measures terrain, none of them says terrain. They're all model data set, because so far there is no satellite that is can wall-to-wall penetrate to the ground and actually see the terrain. Now we have biomass, which will be able to do that. But all the other data sets, they use either JEDI data to model terrain, but none of them actually measures it. So how do you use the uncertainties from those in your ensembled approach?
Well, that's a very good question. So we actually map one of the uncertainty during our prediction phases, but for sure, this is not that kind of uncertainty that you're looking for. The uncertainty is more like how easy the pixel have to be predict, because you have some places which is more sensitive to the vegetation, and which means that most of the data are hard to capture the terrain. So these places could be more higher uncertainty if the terrain is actually there. And also the place with higher slope places, they also have very big uncertainty over there. And to give that one of the derivable of this ensemble approach, that we also try to see what is agreement of each different digital terrain model to one pixel. So you can derive the standard deviation of the terrain in one pixel to actually see that, okay, he's not satisfied. He's not satisfied.
No, but I mean, the disagreement, it still doesn't tell you which data set you're closer to reality, but the ALS data sets, they're probably more correct.
Yep. So you tend to trust those data set more, and then we also see that if we actually over there with the LiDAR spaceborne LiDAR data, to see that how is the close to the spaceborne LiDAR in some area. So that's also a way to find the accuracy of the local. But most of the time, you use the reference digital terrain model from some states. They flew some airborne LiDAR, and then you compare all these differences amongst digital terrain models. So